Explain me your current project and your roles and responsibilities.
In my current project, I am working on a Spring Boot-based microservices architecture that uses Kafka for messaging between services. My role in the project involves designing, developing, and testing the Kafka-based messaging system, as well as integrating it with the microservices. I am responsible for ensuring the system is scalable, fault-tolerant, and meets the requirements of the business. Additionally, I work closely with the other developers and stakeholders in the project to ensure that the system is delivered on time and within budget.
Why Kafka, not any other messaging service like RabbitMQ and JMS?
Kafka has several advantages over other messaging services like RabbitMQ and JMS that make it a popular choice for many use cases. Here are a few reasons why Kafka may be preferred over other messaging systems. 1. High throughput and scalability. Kafka is designed to handle large volumes of data in real time and is highly scalable. It can handle millions of messages per second, making it a good fit for use cases that require high throughput. 2. Fault tolerance. Kafka provides built-in fault tolerance and replication capabilities that ensure that data is not lost in the event of a broker failure. 3. Stream processing. Kafka provides a stream processing API that allows developers to perform complex real-time processing operations on data streams. 4. Durability. Kafka provides long-term storage of messages that can be used for batch processing or data retention purposes. 5. Simple architecture. Kafka's architecture is simple and straightforward, which makes it easy to set up and maintain. Overall, Kafka's combination of high throughput, fault tolerance, and stream processing capabilities make it a popular choice for building real-time data pipelines and streaming applications.
What is the role of Zookeeper in Kafka?
Zookeeper is a distributed coordination service that is used by Kafka to maintain cluster state and to facilitate leader election for partitions. In a Kafka cluster, Zookeeper acts as a centralized repository of metadata about the state of the brokers and the topics. Some of the key responsibilities of Zookeeper in a Kafka cluster include: 1. Keeping track of the broker nodes in the cluster. When a new broker is added or removed from the cluster, Zookeeper updates its registry of brokers. 2. Managing topic partitions and replicas. Zookeeper helps to maintain the list of topic partitions and the replicas for each partition. It also keeps track of the leader for each partition and facilitates the process of leader election if the current leader fails. 3. Providing coordination services for distributed processes. Zookeeper is often used as a synchronization mechanism to coordinate actions between distributed processes in a Kafka cluster. 4. Storing configuration data. Kafka uses Zookeeper to store configuration data for topics and consumers.
Explain me about Kafka topic, consumer group, partitioning, lag, producer and listener in Kafka.
Sure, I'd be happy to explain those concepts in Kafka. 1. Kafka topic. A topic in Kafka is a category or feed name to which messages are published by producers. Topics in Kafka are partitioned and can have multiple partitions. Each partition is an ordered, immutable sequence of messages. 2. Kafka consumer group. A consumer group in Kafka is a group of consumer instances that jointly consume a set of Kafka topics. Each instance in a consumer group is assigned a subset of the partitions of the topic that the group is consuming from. This enables multiple instances of a consumer application to work together to process a large volume of messages in parallel. 3. Partitioning. Partitioning in Kafka is the process of splitting a topic's data across multiple brokers. Each partition is stored on a separate broker in the Kafka cluster, allowing for distributed and scalable message processing. Producers write messages to a partition, and consumers read messages from one or more partitions of a topic. For lag in Kafka is the difference between the current position of a consumer group in a partition and the latest available message in that partition. Lag indicates the amount of backlog in a partition, or how far behind a consumer group is in processing messages. Monitoring lag is important for ensuring that consumers are keeping up with the rate of message production and for identifying potential bottlenecks. 5. Kafka Producer. A Kafka producer is a client that publishes messages to a Kafka topic. Producers can send messages synchronously or asynchronously, and can specify a partition key to control how messages are distributed across partitions. 6. Kafka Listener. A Kafka listener is a mechanism used by Kafka consumers to receive messages from Kafka brokers. Listeners can be implemented in a variety of ways, including using the Java Consumer API or using Spring's Kafka listener annotations. Listeners are responsible for fetching messages from Kafka partitions and processing them.
Can you write code for publishing a message in Kafka topic?
Okay, here is my code.
Write code for the listener of the same message in next service.
Okay, here is my code.
What are the different types of serializers that you can use in Kafka?
In Kafka, there are several types of serializers that you can use to serialize the key and value of a Kafka message. Here are some of the most common serializers. String serializer. This serializer converts the message payload to a string using UTF-8 encoding. Byte array serializer. This serializer simply converts the message payload to a byte array. Avro serializer. This serializer uses the Avro schema to serialize the message payload into a compact binary format. JSON serializer. This serializer converts the message payload to JSON format. Protobuf serializer. This serializer uses Google's protocol buffer's serialization format to serialize the message payload. Custom serializer. You can also implement a custom serializer to handle a specific message format that is not supported by the built-in serializers.
Suppose you have 3 instances of a service, either of them should serve the Kafka message. How will you configure your Kafka for this situation?
To configure Kafka to distribute messages among multiple instances of a service, you can create a consumer group and configure each instance of the service to join that group. Here's how you can do it. 1. Create a consumer group. A consumer group is a logical grouping of Kafka consumers that share the same group ID. To create a consumer group, simply choose a group ID and configure each instance of the service to use that group ID when consuming messages. 2. Configure each instance of the service to join the consumer group. In your service's configuration file, set the group.id property to the chosen group ID. This will ensure that each instance of the service joins the same consumer group and consumes messages from the same Kafka topics. 3. Configure Kafka to distribute messages among the instances. By default, Kafka distributes messages across all consumers in a consumer group using a partitioning strategy. To ensure that messages are distributed evenly among the instances of your service, make sure that the Kafka topic you are consuming from has at least as many partitions as there are instances of your service. You can increase the number of partitions on a topic by using the Kafka command line tools or by configuring your Kafka cluster. With these steps, you can configure Kafka to distribute messages among multiple instances of a service and ensure that each instance of the service is processing messages from the same Kafka topics.
Can we have different number of message listeners and producers?
Yes, you can have a different number of message listeners and producers in Kafka. The number of message listeners that you have determines the number of consumer instances that will be created to consume messages from a Kafka topic. Each consumer instance in a consumer group will be assigned a subset of the partitions for the topic, so increasing the number of message listeners will allow you to scale the consumer group and handle more messages in parallel. On the other hand, the number of Kafka producer instances that you have depends on your application's needs and requirements. In some cases, you may only need a single producer instance to publish messages to a Kafka topic. In other cases, you may need multiple producer instances to increase throughput or handle spikes in message volume. Ultimately, the number of message listeners and producers that you need will depend on factors such as message volume, message size, processing requirements, and available resources.
Give me an example how I can utilize Kafka in food delivery application.
Sure. Here's an example of how Kafka can be utilized in a food delivery application. 1. Order placement. When a customer places an order, the order details such as the items ordered, delivery address, and payment details can be sent as a message to a Kafka topic called orders. 2. Order processing. A set of Kafka message listeners can listen to the orders topic and process the orders in parallel. Each listener can retrieve a subset of the orders based on the partitioning strategy and process them independently. The order processing steps can include tasks such as validating the order, preparing the food, and assigning a delivery person. 3. Delivery tracking. When a delivery person picks up the order, the delivery details such as the driver's name, vehicle details, and estimated delivery time can be sent as a message to a Kafka topic called deliveries. Customers can subscribe to the deliveries topic to receive real-time updates on the status of their delivery. 4. Analytics and insights. Kafka can also be used to capture data about the food delivery process such as the average delivery time, delivery person performance, and customer feedback. This data can be processed in real time using Kafka streams or stored in a data lake for batch processing and analysis.
What is Kafka Streams and Data Lake?
Kafka Streams is a client library that allows you to process and analyze data in real time as it flows through Kafka. It is a lightweight and easy-to-use library that enables developers to build streaming applications that can read from and write to Kafka topics. Kafka Streams provides a powerful API that enables developers to perform stateful processing, windowing, and aggregation operations on data streams. It is designed to work seamlessly with Apache Kafka and supports the same fault-tolerant and scalable architecture. A data lake is a centralized repository that allows you to store and manage large volumes of structured and unstructured data. It is a cost-effective solution for storing and processing large amounts of data in its native format. A data lake can store data from various sources such as databases, files, and streaming sources like Kafka. It can be used for a wide range of use cases such as data analytics, machine learning, and business intelligence. A data lake typically uses a distributed file system like Hadoop Distributed File System, HDFS, or cloud storage services like Amazon S3 or Microsoft Azure Blob Storage. In a Kafka-based architecture, Kafka Streams can be used to perform real-time processing and analysis of data as it flows through Kafka. The processed data can then be stored in a data lake for further analysis and processing. The combination of Kafka streams and a data lake enables you to build a scalable and fault-tolerant streaming data pipeline that can handle large volumes of data in real time.
What are some best practices for optimizing performance when using Kafka streams and a data lake?
Some best practices for optimizing performance when using Kafka streams and a data lake are: partitioning. Kafka Streams uses the partitioning strategy of the underlying Kafka topics for parallel processing. By carefully choosing the partitioning strategy, you can optimize the performance of your Kafka Streams application. For example, you can partition the data based on the key field to ensure that all messages with the same key are processed by the same Kafka Streams instance. Windowing. Kafka Streams supports windowing operations for processing streams of data over a fixed time interval. By using windowing, you can reduce the amount of data that needs to be processed and improve the performance of your Kafka Streams application. Caching. Kafka Streams provides a built-in caching mechanism that allows you to store intermediate results in memory. By caching frequently accessed data, you can reduce the amount of data that needs to be read from the data lake and improve the performance of your Kafka Streams application. Monitoring and tuning. It's important to monitor the performance of your Kafka Streams application and tune it based on the observed performance metrics. You can use tools like Apache Kafka's built-in monitoring tools, third-party monitoring tools, and custom metrics to monitor and tune the performance of your Kafka Streams application. Scaling. Kafka Streams supports horizontal scaling by allowing you to add more instances of your Kafka Streams application to handle increased data volumes. By scaling your Kafka Streams application, you can ensure that it can handle large volumes of data and maintain low latency processing. Optimization of data lake storage. It is important to choose the appropriate storage technology for your data lake to optimize the performance of your Kafka-based streaming data pipeline. Technologies such as columnar storage, compression, and indexing can help to optimize the performance of your data lake.
How partitioning helps in performance improvement.
Parallelism. By partitioning a Kafka topic, you can enable parallel processing of messages by multiple consumer instances. Each partition can be assigned to a different consumer instance, which can then process messages from that partition independently of other consumer instances. This increases the overall throughput of the consumer group and helps in scaling out the processing of messages. Load balancing. Partitioning allows for load balancing of messages across multiple consumer instances. Since each partition is processed independently by a single consumer instance, the processing load is evenly distributed across all consumer instances. This helps to avoid overloading any single consumer instance and ensures that the processing workload is distributed evenly across the entire consumer group. Ordering. Partitioning can also help in maintaining message ordering. By ensuring that all messages with the same key are processed by the same consumer instance, partitioning can help to ensure that messages with the same key are processed in the order they were produced. This can be particularly important in use cases where message ordering is critical. Flexibility. Partitioning allows for flexibility in scaling up or down the number of consumer instances. As the message volume increases, more consumer instances can be added to handle the additional load by assigning partitions to the new consumer instances. Conversely, as the message volume decreases, consumer instances can be removed by reassigning partitions to the remaining consumer instances.
Write code for making partitions in topic in Kafka.
Here's an example code snippet for creating a Kafka topic with partitions using the Kafka command line tools. This command creates a topic named myTopic with 3 partitions and a replication factor of 1. The Zookeeper option specifies the Zookeeper connection string. The replication factor option specifies the number of replicas for each partition, which determines the fault tolerance of the topic. In this example, we have set the replication factor to 1, meaning that each partition will have only 1 replica.
What happens if I make replication factor as 2 instead of 1?
If you set the replication factor to 2 instead of 1 when creating a Kafka topic, each partition in the topic will have 2 replicas stored on different brokers. Setting a replication factor of 2 provides fault tolerance for your topic. If one broker fails or becomes unavailable, another broker with a replica of the partition will take over, ensuring that the topic remains available and that data is not lost. It's recommended to have a replication factor of at least 2 in production environments to ensure fault tolerance and avoid data loss. However, increasing the replication factor will also increase the amount of storage required for storing the replicated data, as well as increase the network traffic and CPU usage for the Kafka brokers handling the replicas.
What are you referring as broker in your answer?
In Kafka, a broker is a server instance that stores and manages the topic's partitions and its replicas. A Kafka cluster consists of 1 or more brokers working together to manage the topic's partitions and replicas. Each broker in a Kafka cluster is identified by a unique numeric ID called the broker ID. When creating a topic, you can specify a replication factor, which determines how many replicas of each partition are stored across different brokers in the cluster. In the context of the previous answer, when I mentioned different brokers, I was referring to the fact that each replica of a partition in a Kafka topic is stored on a different broker in the cluster. If one broker goes down, another broker with a replica of the partition will take over and serve the topic's data to consumers, ensuring fault tolerance and high availability.
Thank you for sharing your knowledge and experiences with me today. It was great to learn more about your skills and expertise in Kafka. We will be in touch regarding next steps in the hiring process.
Thank you for the opportunity to discuss my experiences with Kafka. I appreciate your time and consideration, and I look forward to hearing from you soon.